Welcome back everyone. In today's video, I'll be explaining AtCoder Beginner Contest 321. I'll explain the problems from C to F. I've provided the correct Python codes in the video description, so please check it out after you've listened to my explanation. Let's get started with problem C. The task is to find the case smallest number among 321 like numbers. The definition of 321 like numbers is numbers whose digits are strictly decreasing from top to bottom. So 321 and 96,410 and 1 are the examples, and 123 and 2,109 and 86,411 are the counterexamples. How can we solve it? The most important notion is that 321 like numbers are not so many. We've concluded it by guessing the condition of being 321 like numbers is strict. And for example, the maximal number is a 10-digit number starting with 9 ending with 0, and any other 10-digit numbers are not 321 like numbers. So our strategy is like this. First, write all the 321 like numbers down and append them in list S. Then sort S in ascending order and print the case number of it. The last thing to think about is how to write them all down. We have many ways, but I will introduce you to the ways of constructing them from lower digit numbers to higher digit numbers. First, we begin with 321 numbers with one digit, like from 1 to 9. Then, to get two-digit numbers, we try every pair of a 321 number with one digit, which is n here, and a one-digit number for the one place, which is a, and just synthesize n and a like this. This generates all the 321 numbers with two digits. So try it up to 10 digits, and finally we get all the 321 like numbers. Then I will end the explanation of problem C. Let's proceed to problem D. In short, our target is to calculate this sigma. It contains two variables I and j, so we need some improvement. First, since the minimum function is little tedious, so we remove it. This is easy to calculate, like m times sum of a plus n times sum of b. But the value might be larger than the target, so we must subtract something. To be precise, for each I and j, if ai plus bj is at least p, then we subtract ai plus bj minus p from the sum. Here we get an inequality with two variables, and we have a typical approach for it. I'll introduce you. That is, we should do a brute force search for one variable and do bisect for the other. I'll explain it with an example below. But first, let's see the inequality and solve it for AI. Then we fix bj. For fixed bj, the expression p minus bj is just constant, and so we easily find how large the variable a should be. After sorting a, we find the minimum index I with ai is at least p minus b by bisect. So we can compute the sum for fixed bj collectively. But to compute it effectively, we need to prepare the cumulative sum for a. But I leave the details to you. This ends problem D. Let's proceed to problem E. This is a question about a complete binary tree. Our task is to count the number of vertices with the given distance from a given point. This problem has so many test cases, so we must solve each in logarithmic time. But to be worse, the tree size is enormous for each case. This problem may be difficult if you are not familiar with complete binary trees, but let's get started. First, we define depth for convenience. We define vertex 1 as the root of the tree, and the depth of the tree is aligned like this. Here, we have tips to calculate depth of an arbitrary vertex. For vertex n, the depth is the length of n in base 2 system minus 1. So it is easy to calculate. Our task is counting vertices, but we can't count them one by one. Therefore, we divide them into groups. Look at the graph. The first group, f of 0, is below the given vertex x. More precisely, vertices in f of 0 are children of x with distance k. We denote x1 the parent of x, and the next group, f of 1, is below x1 connected with the left branch. Like this, every time we climb up from x, we encounter a group of required vertices f of I if looking at the adjacent branch. We denote them fi from bottom. Then our target is to calculate the sum of fi. This seems to be acceptable if easy to calculate f of I because I ranges from 0 to the depth of x denoted by d here, and it's about log of x. So our concern shifts to the calculation of f of I. To calculate f of I, we define the function count of x and t as the number of children of x with distance t in the complete binary tree. This is a useful function for calculating children for fixed vertex and fixed distance. After slight considerations, the minimum index of children of vertex x with distance t is expressed as 2 raised to the power of t times x, and the maximum is expressed as 2 to the powers of t times x plus 2 to the power of t minus 1. Considering the graph size n, we take the intersection of the interval and 1 to n. We leave the details to you, but we can implement it in all of 1. Now we are ready to calculate f of I. Suppose we climb up from x I times, and we are in xi. Then the distance between f of I and xi is k minus I, denoted by ti, and we can know the number of all the children of xi with distance ti, computing count of xi and ti. But we must subtract children passing x of I minus 1 from it. So we subtract count of xi minus 1 and ti minus 1. This is f of I. This ends problem E. Finally, let's proceed to problem F. This is a typical problem called subset sum problem, and you know dp is an effective way to solve it. In this problem, we have two operations of adding number x and discarding number x, and we can solve the adding operation part so easily. In fact, we define dp as the state before adding x and dp prime as the state after adding x. And we can write transitions as the bottom left expression. But how about the discarding operation? Surprisingly, the answer is already on our hand. Adding a number and discarding it are inverse operations, and to add x means to compute dp prime from dp, and it can be paraphrased as solving transition equations for dp prime. Therefore, to discard x, all we have to do is compute dp from dp prime and solve transition equations for dp. So we can get transitions for discarding operation from those of adding operation. Now you write the correct code paying attention to the role of dp and dp prime. I'll finish the explanation of problem F, and with that, I've completed all the explanations. If you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching the video.